My cognitive psychologists in training. I am here to present a little bit more on visual perception to get you through the rest of the week. I will follow up with some more about visual perception on Monday, and I'll be back to see you on Wednesday. So let's continue our discussion with the different types of grouping rules that were identified by the Gestalt psychologists to help us figure out where one object ends and another begins and how to separate that out from the background. So I mentioned several different laws. The laws of good continuation, texture segmentation, similarity, proximity, and closure. And as we saw at the end of class, each of these can be demonstrated fairly easily. So here's the law of texture segmentation. You can see one square here by the differences in texture, another here. As I mentioned at the end of class, here is the law of similarity. We tend to group similar objects together. So you might be inclined to see this as two different squares made of two different types of shapes rather than rows that go from one shape to another. This is the law of closure. Now you'll notice that you can probably very easily see an arrow in this figure. Now, of course, I hope you know that there is no actual arrow that is there. In this particular case, our brain takes all of this white space and treats it as if there is a white arrow that is blocking all of these other circles. Now, here's what else is really critical. Now, not only do we see an arrow coming out of this white space, we assume that it's blocking whole circles. So if we looked behind this white space, we would expect to find the rest of this particular circle rather than just, well, in this case, I'm basically pointing at Pac-Man. But we assume that the circles that are being blocked are actually circles and not parts of circles, as shown here. This is the law of proximity. In this particular case, because these squares are closer together than these squares, we tend to perceive these as two different groups. Here's another example of the law of similarity. We see a cross that's kind of cutting between different groups of circles. We're more likely to group these together because they're similar and these together because they're similar. Again, here's our law of good continuation. We're going to perceive this as AOD. This line continues on. It's not going to sharply go up towards C, and we see this as COB. So we see lines as continuing smoothly on. They don't suddenly change direction on us. Here's another case of the law of closure. We see a panda in this figure, even though part of the panda is being made with white space. Now, this is a really interesting question because sometimes the laws are not so clear-cut. What happens when the laws conflict? So, for example, here in A, we have triangles being paired with a square and another group of squares. Now, this square is separate from this square, so the law of proximity wants us to create two different groups here. But the square probably has more in common than these other squares. So what wins? Proximity or similarity? Here, same sort of idea. What matters? Proximity or similarity? In this case, similarity probably matters more. I'm more inclined to group these together because they're colored in, and these ones because they're not. Now, everybody's going to be a little bit different, but researchers Quinlan and Wilton back in 1998 actually looked what happened when laws like proximity or similarity come into conflict. Generally, we start with proximity first. So for example, we might group these together. If we find out that there's a mismatch, we're going to move on to similarity whenever possible. So proximity has a tendency of overruling all other laws, and if proximity doesn't work, as it may not necessarily do here, or here in particular, we're going to default to similarity. And so even though this probably fits better with this, because they're so far apart, this is going to probably be grouped with this, even though it's not colored in, because they're similar to each other. So we use these grouping principles to help perceive a figure from its background. And so one of the ways that the Gestaltists did this was with reversible figure ground images here. So here you are either looking at what could be a vase or a candlestick and two faces. Now here's what's really important. You can't see these both at the same time. Now I know what you're thinking. Wait a minute, Dr. Gilchrist. Yes, I can. But I'm going to say you really can't. Your perception constantly flips back and forth between them. And here's how we know. Generally, we're going to find that the figure has form. It has contours and it's in front of the ground. So when I'm looking at the faces, I'm not really looking at the vase anymore. It looks like white faces against an orange background. But once I start focusing on the vase, it's against a white background. So we're constantly shifting back and forth and back and forth between the vase or the faces serving as the figure or the ground. So the question becomes, well, what next? How do we figure out object features? So we've grouped objects and edges and we've separated the object from its background. Now we actually need to perceive color and depth. So we're going to start with color vision. Color vision is a really important thing that helps separate one object from the background. So for example, right now I'm looking in my room at my purple yoga mat that is hanging off of my doorknob. I know that the yoga mat is separate from the door because my yoga mat is purple and my door is brown. So color can help us separate objects from the background, and it can also help us with object recognition. And there are three important aspects related to color. We have the concept of hue, which is the color itself. So is something blue? Is something green? Is something yellow? Is something red? We also have the concept of brightness. This is about the perceived intensity of light. So a light blue is going to be more bright and it's going to be a little less intense, like a bright blue. On the other hand, a dark blue, like a navy blue that's almost black, has no intensity of light. So we're looking at brightness, how much light or dark is present in that color. And then finally, we have saturation. Is the color vivid and bright blue like you see here, or is it more muted, like this blue-gray? So we have hue, brightness, and saturated. So how do we see color? We see color because of cones. And it turns out that we have three different types of cones that are present in our retina. And each of them is designed to have a particular peak wavelength. The first is our short wavelength cones. These are maximally active when they're presented with blue or purple light. And that peak is at about 437 nanometers. So sometimes we call these blue cones, even though they respond to a lot of the colors besides blue. You can actually see here in this figure that they do show some responsiveness to colors like green. We have green cones or medium wavelength cones, which have a peak wavelength of about 533 nanometers. But again, even though we call this a green cone, note in the figure that it's responsive to blue, also responsive to yellow, orange, and red. And then finally, we have long wavelength cones, which corresponds more to 560 nanometers or about yellow-orange. These cones respond best to those longer wavelengths like yellow, orange, and red, that they do also respond to a little bit of green and even a little bit of blue. So even though we call them blue, green, and red cones, they don't just respond to those colors alone. Now I'm sure you're curious. Well, Dr. Gilchrist, that's great. We've got blue, we've got green, we've got red, but what about purple? What about pink? What about brown? How do I see those? Well, the thing is that every single color that you could potentially encounter is made up of a combination of red, blue, and green wavelengths. So for example, when they're all maximally activated, you get white. On the other hand, when they're minimally activated, we get black. So the idea is that every color that you could possibly encounter is made up of different components of red, green, and blue cones. And so we can see other cones by the relative stimulation of each type of cone. That's how we figure it out. But it gets a little bit more complicated. One of the things that people have discovered is that trichromacy doesn't really account for the finding of something called a negative afterimage. So I'm going to show you an example of this using my computer. Let's see if the internet works. Come on. We got to do this for people. So I'm going to pull up a YouTube video. So we're getting a little meta here. We're watching a YouTube video in a YouTube video in this particular case. So we're going to play this and fast forward. I'd like to stare at a particular colored flag. Stare at the white dot in the center for as long as you can. Keep staring. Stare at that white dot. Try your best not to blink. Keep going. You can do it. I believe in you. Oh, and if you did this right, as that shifts to white, you should have been able to see a red, white, and blue flag. Trichromacy doesn't account for how that happens. So back in 1878, Herring came up with the concept of opponent process theory, which is basically the idea that our processing of colors tends to occur in three opponent pairs. Red opposes green, so if we look at red too long, our cones get oversaturated and we kind of shift over to green. Blue opposes yellow because that's a combination of short wavelengths versus medium and long wavelengths. Red versus green is long versus medium. Blue versus yellow is short versus medium and long. And black and white, this opponent process is based on none of the color cones versus all of the cones. So we do have these three opponent processes going.